Okay, so our final speaker today is Andreas Ringwald. He's going to tell us about the quest for axions and other WISPs.
So thank you very much for the invitation to speak here. It's in fact the first time I'm in Cambridge. I was often to Oxford, but never in Cambridge, so very nice. So how do I get forward?
You have to.
I'll just do it here. Thanks. So there are plenty of dark matter candidates spanning a huge range in masses and couplings. So there are and two classes in this huge range of dark matter candidates stand out because of their convincing physics case and the variety of experimental and observational probes. So the one class which is most often discussed, I guess, are weakly interacting particles, WIMPs, such as neutralinos. But there's also very nicely physics-motivated class of very weakly interacting SLIM in the sense of ultralight particle, so-called WISPs, such as axions. And the plan in my talk, I will concentrate on these lesser discussed particles, namely on axions and other WISPs. So I will first try or talk about the physics case for axions and axion-like particles, which I will call ALPS. And then I will talk about the nice fact that there are many different experimental probes and searches for axions and axion-like particles going on, which will deeply dig into the good motivated parameter space of axions and axion-like particles. Now the axion was first introduced not as a solution for a cosmological problem, of a problem in cosmology, but rather in order to solve a problem in strong interactions or in QCD. Shortly after the invention or the proposal of QCD as the theory of strong interactions, it became clear that the fundamental parameters of QCD are not only the strong coupling alpha S, the quark masses m up, m down, and strange, and so on, but also there's another fundamental dimensionless angular parameter, theta bar, which consists of a vacuum angle plus the argument of the determinant of the quark mass matrix. So this dimensionless parameter, angular parameter theta, multiplies the topological charge density in QCD, which is essentially the contracted gluon field strengths contracted with the dual gluon field strengths. And this term violates, it's essentially in column magnetic and electric fields expressed as EA dot B dot. BA violates T and P and thus CP, and so one in order to measure this quantity or find a value of this quantity, one has to look for T and P violation in flavor conserving interactions. And the most sensitive probe of T and P violation in flavor conserving interaction is the electric dipole moment of the neutron. Now, experimentally, we know that the electric dipole moment of the neutron is less than 3 times 10 to the minus 26 e centimeter. However, if one calculates this in QCD and expressed in terms, it will be, of course, proportional to theta bar and some hadronic quantities like the the quark masses and the neutron mass, and numerically this factor is of course something like typically for strong interactions, namely of the size of the proton or so 10 to the minus 16 centimeter times E times theta bar. So normally, because this is just an angular parameter comprised or given by a sum of this vacuum angle plus this arc determinant, one would expect that this angle is somewhere typically between 0 and pi, something order unity. However, if one compares this now with this upper bound for the electric dipole moment of the neutron, one finds that experimentally it should be less than 10 to the minus 9. So this was the strong CP problem, because other fundamental parameters in QCD are of course order unity, even the strong coupling, and here this is even now, this is because this is a sum of a vacuum angle plus something which comes from flavor physics, so this is some miracle. Shortly, Roberto Pecce and Helen Quinn, they found a nice solution to the strong CP problem, also in the early days of QCD. This was based on the observation that the vacuum energy in QCD, which you can infer from the chiral QCD Lagrangian, from the low energy effective theory of QCD, has a localized minimum at vanishing theta parameter. So it starts its expansion around the small value of theta bar starts with the quadratic term. So this means if theta were a dynamical field, its VEF would be 0, and there would be no, so if it's just a dynamical field, the vacuum expectation value would be 0, and there would be no strong CP violation, no contribution of strong interaction to the electric dipole moment of the neutron, for example. Now, the general idea then, which was exposed by or proposed by Roberto Pecce and Helen Quinn, was they introduced a scalar field, or essentially a pseudoscalar field, as a dynamic theta parameter, which respecting a nonlinearly realized nu1 Pecce-Quinn symmetry, that means a shift symmetry that you can just add to this a constant, and the Lagrangian should be invariant, broken only by a coupling to Chi-Chi dual. So it should be coupled like this theta bar to this Chi-Chi dual. And because this is a field of mass dimension 1, you should normalize this by the so-called Pecce-Quinn scale or decay constant of the axion in analogly to pion physics. So if you have such a field, then you can eliminate this theta bar by a shift. You just make this shift in order to eliminate that, and then QCD dynamics leads to a vanishing VEF for the shifted field. So there's P and T and CP are conserved. So this is the solution of the strong CP problem. Of course, there is also a particle excitation around this VEF. And this particle excitation around this VEF is the Nambu-Goldstone boson of this symmetry breaking, and this has been called axion by Frank Wilczek, just because it solves a problem in QCD which has to do something with an axial current. The strength of the interactions of the axion with the standard model is controlled by the Pecce-Quinn, by the Pecce-Quinn scale Fa. Now we see, because of the mixing of this axion with the neutral pion, described again by the chiral QCD Lagrangian, the axion is in fact not a real Nambu-Goldstone boson, but just a pseudo-Nambu-Goldstone boson with a seesaw relation between the chiral symmetry breaking scale m pi f pi, where this is the pion mass and this is the pion decay constant, and the Pecce-Quinn scale Fa, which means now if the Pecce-Quinn scale is large, very large, so say 10 to the 9 GeV, then the mass of the axion is milli-electron volt. This axion has a universal coupling to photons and to photons, which is similar, like the interaction with gluons goes like F dual, now where these are now the electromagnetic field strengths and its dual, and this coupling constant is given by alpha over 2 pi 1 over Fa. So it's also so for large Fa, this coupling is very small. For 10 to the 9 GeV, it's 10 to the minus 12 GeV to the minus 1. So for a large Pecek-Wien scale, the axion is a prime paradigm of a WISP. And of course, it solves the strong, so the solution of the strong CP problem does not fix this scale at all. So for any scale FA, the axion solves the strong CP problem. However, phenomenology tells us, and this has been worked out already, starting immediately after the proposal of the axion. One started first with analyzing beam dump experiments and so on, but soon one realized that the best limits, they come from astrophysics, namely from the lifetime of globular cluster, of stars in globular clusters, which forbid energy loss due to axion production. And the best model independent limit comes from the burst duration of the supernova 1987A. And so the axion, we know for the axion that the decay constant should be larger than 4 times 10 to the 8 GeV, and so correspondingly the mass should be less than, say, 16 milli-electron volt. So the axion is indeed a WISP. So it's now, but a few years later, it was realized that for Fa larger than 10 to the 9 GeV, the axion can also play a very dominant role in cosmology. Namely, axions are then produced predominantly non-thermally in the early universe. And one of the dominant productions, non-thermal production, goes via the so-called vacuum realignment, which means that in the early universe, in the very early universe, the homogeneous mode of the axion field will be frozen at a random initial value, theta I times Fa, because of the cosmic expansion. As long as the time is less than the inverse axion mass. However, if the time becomes later than the inverse axion mass, the axion is oscillating around 0, where the oscillation frequency is given by the axion mass. And what was found by these authors, of course, that the energy density of these oscillating field scales like non-relativistic dark matter, and this can also be understood that the classically coherent oscillating scalar fields, they are essentially a coherent state of extremely non-relativistic dark matter. That means cold dark matter. So there is a natural non-thermal production mechanism for axions in the early universe. And if one calculates the energy fraction in axions, in the case that the reheating temperature after inflation is below the Pecek-Wien scale, and there is no dilution by late decays of particles beyond the standard model, one finds that one could saturate the present dark matter density if the decay constant is of the order of 10 to the 12 or 10 to the 11 GeV, and the vacuum, the initial vacuum angle is of the order of pi. If the reheat, so here is some free, here is some freedom that the initial, if the decay constant would be much larger than 10 to the 12 GeV, for example, gut scale decay constant, then one would have to fine-tune this initial value, or this initial value should take a special value in order not to have too much axion dark matter in the universe. In the opposite case, if the reheating temperature after inflation is above the Pecek-Wien scale, the initial misalignment angle take on different values in different patches of the universe, and one has to average over this. So then, in this case, one doesn't have this freedom. So then essentially this fixes the axion mass if one wants to have the axion to be the dark matter. And in this case, but in this case also decay of cosmic strings and domain walls may provide for additional sources for axion dark matter, so that even for 10 to the 9 or less, 10 to the 9, that even for 10 to the 9 GeV Peccei-Quinn scale, one could have dark matter. Other bosonic WISPs, such as axion-like particles, which I will refer to now for pseudo-Nambu goldstones from further U1 Peccei-Quinns, which are not coupling to Chi-Chi dual, would also be produced via the vacuum realignment mechanism. And again, one finds that for light enough particles, so a particle below an electron volt, you need decay constants in the 10 to the 11 GeV range to saturate the present dark matter density. So there is a natural range for axion and axion-like particle cold dark matter, the so-called cosmic axion window between 10 to the 9 GeV and decay constants for the axions, or Peccei-Quinn scales for the axion, or for axion-like particles up to 10 to the 12 GeV, which is also sometimes called the intermediate scale, because it's about the square root, the geometric mean between the weak scale and the Planck scale. So for this, you get naturally axion and ALP cold dark matter. Correspondingly, there is a large search space for axion and ALP cold dark matter in the photon coupling. The photon coupling, as I have shown for, will go like alpha over 2 pi 1 times these decay constant. And if one looks, so in this, so here is, I have plotted the two photon coupling versus the mass of axion-like particles, or the axion. The axions, they live in this band because they have the universal prediction for their coupling to photons. But everywhere in this shaded region, axion-like particles could also be the dark matter. Now, still, we have no, so why should the scale be, so this is just phenomenologically driven or cosmologically driven. Why should the Peccei-Quinn scale be between 10 to the 9 and 10 to the 12 GeV? Is there anything special about that? So why should be the Planck scale or the Guts scale? So there's one bottom-up theory motivation for the intermediate scale, which I find quite intriguing. So if you just look now for an embedding of this axion theory in a UV completion of the standard model, you can make a minimalistic global U1 Peccei-Quinn extension of the standard model by introducing, first of all, just extending the standard model by a singlet complex scalar field plus a vector-like color triplet. It's similar to models which have been proposed by Kim, Schiffman, Weinstein, and Zakharov, and right-handed singlet Majorana neutrinos. And if you assign them Peccei-Quinn charges like that, then the only allowed terms in the Lagrangian in the Yukawa interactions involving the Peccei-Quinn charged fields are given by this. So this gives the normal mass term for the charged leptons. This gives a Dirac mass term for neutrinos. This gives a Majorana mass term for neutrinos, and this gives a mass term finally after symmetry breaking for this vector-like color triplet. And this is the most general Peccei-Quinn invariant scalar potential, which involves the Higgs, this hidden complex scalar field, which will get a VEF V Peccei-Quinn. And here is a Higgs portal term, mass dimension 4 term, which couples these both Higgses. And this simple model can explain simultaneously for intermediate scale vacuum expectation value of this singlet complex scalar field can explain simultaneously the absence of strong interaction, where now the Peccek-Wien scale is in fact this symmetry breaking scale V Peccek-Wien. The axion itself is the Nambu-Goldstone boson from the symmetry breaking. So I expand this sigma field around the WEF, and the angular mode is the axion, which couples to Chi dual via the anomalous triangle graph of this vector light exotic color triplet. So there is no strong CP violation. There is you can explain the dark matter by the axion if this Peccek-Wien scale or this WEF is between 10 to the 9 and 10 to the 12 GeV. The masses of the active neutrinos you can calculate here, because if you get, so to say, a seesaw between this Majorana mass term and this Dirac mass term, which involves now the corresponding Yukawa couplings, times V squared over V Peccek-Wien. This is the electroweak WEF, and this is the Peccek-Wien WEF for Peccek-Wien WEF of 10 to the 12 GeV. And for reasonable Yukawa couplings, you get the 0.06 electron volt. So this is the normal seesaw effect. You get the baryon asymmetry of the universe through thermal leptogenesis by these decays. And this works best, as we well know, if the masses of the right-handed neutrinos are larger than 10 to the 9 GeV. So this WEF, this WEF should be of the order of 10 to the 12 or so. And the stability of the and you get even the stability of the electroweak vacuum through the scalar threshold effect through this Higgs portal term. So this is a very nice theory which could explain everything. Only inflation is not involved in that, but this explains dark matter and so on. And the only scale is this intermediate scale in this model. Now I come to a top-down theory motivation for intermediate scale. This is not so easy. So, here I take the string theory, string phenomenology. The 4D low-energy effective field theory emerging from string theory predicts very natural candidates for the axion, often even an axiverse containing not only the axion but additional axion-like particles. So one of these axions and alps, they arise as Kaluza-Klein zero modes of the 10D antisymmetric tensor fields, where the latter belong to the massless spectrum of the bosonic string. So the shift symmetry in this case you get from gauge invariance, and the number of in 10 dimensions. The number of alps depends on the topology, on the number of cycles which the extra dimensions have. The Peccek-Wien scale for this closed string axions, unfortunately, is of the order of the string scale. So it's of the order of the Gatzgau between the Gatt and the Planck scale in the heterotic string case, but it can be typically lower even of the intermediate scale, 10 to the 10 GeV in 2B compactifications, realizing brane worlds with large extra dimensions. So in these branches you could expand, but often in these theories the cosmology is not standard, and sometimes you have or often you have a cosmological moduli problem if the string scale is so low. However, there are other axion-like particles also arising in string compactifications, namely they arise as Nambu-Goldstone bosons from accidental Peccek-Wien symmetries, which appear as low-energy remnants of discrete symmetries from the compactification. In this case, the Peccek-Wien scale is decoupled from the string scale and can be intermediate, but it's hard to predict even the value. Now, I have told you now a very strong physics case for axions. We have seen that in the string compactifications we can have additional axion-like particles. So is there also a phenomenological motivation for axion-like particles? And there are some hints which are there are some hints of axion-like particles which I would like to mention here. So first of all, one hint is the anomalous very high energy transparency of the universe. Very high energy photon spectra from distant active galactic nuclei should show absorption features due to pair production at the extragalactic background light. So, it's clear that this should happen. However, it seems that this prediction is in conflict with observations. So, as has been pointed by many authors since the last few years, in fact, there are. So this gives a summary of all the sources observed of HEN spectra observed with imaging atmospheric Cherenkov telescopes, and many of the sources extend in energy into the optical thick regime. So the spectra above this blue line, which corresponds to an absorption of e to the minus 1, is e to the minus 2, e to the minus 3, e to the minus 4. They should show absorption features. But if you look into the spectra, then there is obviously the absorption feature is missing. Also, most of these data points, the black are the directly measured data points. Most of these data points come from the optically thick regime, and if one corrects for the absorption to determine the intrinsic spectra, the intrinsic spectra even tend to show an uprise. A possible explanation of this fact would be could be given in terms of photon-Alp conversions in astrophysical magnetic fields. In astrophysical magnetic fields, due to these two photon interactions, a very high energy photon could oscillate with this probability into an axion-like particle, which can traverse the extragalactic background light without being absorbed, and can reconvert into a photon and can be seen then in the Earth. And in fact, this can help to understand or fit the data much better than before. So here recently a group has determined a lower bound on the axion photon, on the Alp photon coupling which should be fulfilled if you want to explain the absence if you want to explain the very high energy photon spectra of distant sources, and this is the region which is so to say favored by this. Here is the mass and here is the coupling. Now, so in numbers, the axion or the Alp photon coupling should be larger than 10 to the minus 12 GeV to the minus 1, and the mass should be less than 10 to the minus 7 electron volt. There are more astro hints for intermediate scale axion and Alps. For example, anomalous cooling of white dwarfs has been claimed to be seen in not only in the white dwarf's luminosity function, but also in the period degrees of pulsating white dwarfs, and in this case, it's not the photon coupling which is involved, but the coupling to the electrons. But for these constants of order unity, you get required Pecek wind scales of the order of 10 to the 9 if you want to explain this. Tomorrow we will hear a talk by Joe Conlon about hints of relativistic Alp background dark radiation in CMB, which is generated by modulus decay, and the Alp decay to photons in magnetic fields of galaxy cluster. For example, the coma cluster may explain the observed X-ray excesses. Now, we have seen, so there's quite a strong physics case to look for axion and Alps with decay constants in the intermediate scale range. Fortunately, this range can be searched for in the foreseeable future, in the next 10 years, or can be attacked with different means, namely with haloscopes, where one is directly looking for dark matter axion and Alps, with light shining through a wall experiments, where one is doing the production and detection of axion-like particles in the laboratory, and with helioscopes, as I will show now in the last few minutes. So haloscope searches, these have been proposed by Pierre Sikivi in '83. So the idea is one uses again the two photon coupling of the axion, so of an Alp. If the axion of the Alp is a dark matter, it can convert into a real photon in a microwave cavity placed in a magnetic field. So here is the microwave cavity placed in a magnetic field. So the magnetic field is a virtual photon, and the real photon can appear. And of course, the frequency of the real photon will be exactly the mass of the axion or the axion-like particle. So the best sensitivity you get if the mass equals to the resonance frequency of this cavity, because in this case the power output, which will be proportional to the coupling squared times the magnetic field squared times the the energy density of dark matter and the volume of the cavity, but it will be also proportional to the quality factor of the cavity, and this can be of the order 10 to the 5 or so. So you can enhance this. The bad thing is, of course, that you have to tune the cavity. Then you have to, because the cavity has one ground frequency, say a gigahertz, and then you have to detune the cavity in order to scan a whole parameter range if you want to keep this sensitivity. So there's an ongoing experiment, the ADMX experiment at the University of Washington in Seattle, which exploits a high Q cavity in an 8 Tesla superconducting solenoid. The search starts at 1 gigahertz towards higher frequencies. And here at DESI we are doing a pilot study, so-called WISP DMX, which will exploit a high Q Hera proton accelerator cavity. One of these, even more of them fit into a H1 solenoid, which has only 1.1 Tesla, but we can start our searches 208 megahertz at smaller frequencies, where the power output inversely scales with the axion mass, so we don't lose so much. So this is so we are doing at the moment a pilot study, and have started without the magnet to look for wispy cold dark matter with this experiment. There is a proposed, so the problem with these experiments is that you have to tune to the cavity in order to use the resonance effect. Therefore, recently we proposed a broadband dish antenna search, which can really go broadband. The idea is that non-relativistic dark matter axions and Alps can be converted or are converted into monogrammatic photons emitted from the surface of a spherical dish antenna placed in a background magnetic field. So if this is placed in the background magnetic field, the axion, again, it excites the photons in the spherical dish, and the photons from the spherical dish are focused in the center, where you can place a broadband detector, and the power at the center is now enhanced, so to say, by the area of the dish. And again, such a big 1 square meter dish or so would nicely fit into this Hera H1 solenoid. Now this is the sensitivity of the microwave cavity ADMX and dish antenna haloscopes. Here's the mass of axions or axion-like particles. Here's the two-photon coupling. The gray area has already been probed by ADMX, and this green so ADMX has also even already dipped deeply into the axion preferred QCD axion preferred region, and this green region is the one which they can probe within this decade. The green region can be assessed by dish antenna experiments. So one can just scratch, so to say, the upper range of the axion line, but one can probe also for other dark matter. I will skip this and go directly to the light shining through a wall searches. These are the most sensitive poorly lab experiments up to now. So the idea is to send laser line along a dipole magnetic field and place a wall in the middle of the experiment and have a magnetic field again on the other side, and here the axion or axion-like particle can in the magnetic field again go into a real photon which can be detected then. The most sensitive light shining through a wall experiment up to now was the Any Light Particle Search 1, ALPS 1 at DC, which used one superconducting Hera dipole, a 5 Tesla dipole, 1.2 kilowatt CW green laser, where we used we had a collaboration with people from the Albert Einstein Institute in Hanover, which are building also the LIGO gravitational wave laser, and just a CCD camera at the end. Since February this year, we got green light to start towards extension of ALPS to ALPS 2, where final data taking is planned for 2017. So the idea is now to increase the magnetic length substantially. We want to use 10 plus 10 superconducting Hera dipoles, 10 before, 10 after the wall, and place them in one of the straight sections of Hera. We have to move them then from the round sections to the straight sections. Then, as a laser, we want to store before the laser light in a cavity. We want to store 150 kilowatt infrared laser light, and want to resonantly regenerate behind the wall. So we have to frequency lock these two cavities to the same frequency. Then we can use the resonant regeneration behind the wall. So the sensitivity of these experiments is the following: of light shining through a wall. So this is the state of this was the state of the art, or the best experiment up to date is ALPS 1, which is still deeply in the excluded region. But the next step is this line. So we envisage an improvement by a factor of 3,000 in sensitivity in this coupling, and in particular we can probe large of this range where one could explain where one could explain the anomalous TV transparency of the universe with axion-like particles. So this region can be probed now directly. So we can do, instead of the very high energy photons in the universe, they make, so to say, light shining through a wall, where the wall is the extragalactic background light. We have the same kind of B.L now in the laboratory, because in our case the length is small but B is large, and in the universe B was quite tiny but the length was enormous. but both are in a sense similar. Now, finally, I come to the helioscopes. So the most sensitive helioscope up to now was the CERN Axion Solar Telescope CAST, which used the superconducting LHC dipole magnet pointing to the sun and looking for axion produced in the center of the sun. Axion produced in the center of the sun have kilo electron volt energies, therefore you need X-ray detectors. And this experiment, there is now a proposed successor, the so-called International Axion Observatory. This month we have given a letter of intent to the SPSC at CERN for this axion experiment, for YAXO. This will then now no more. This will make an end to using just recycle things from accelerator physics. Here one wants to have a dedicated superconducting toroidal magnet with a much bigger aperture than CAST, but with the same kind B.L. One want to use extensive use of X-ray optics and low background X-ray detectors. And with this experiment, one can improve the limits from CAST, which were here at 10 to the minus 10 TeV to the minus 1, by nearly 2 orders of magnitude, and also deeply go into the QCD axion plane. So I come to my summary. There's a strong physics case for axion and ALPS. So the solution of strong CP problem gives a particularly strong motivation for the existence of the axion. For intermediate scale decay constant, the axion and the ALPS are natural cold dark matter candidates. And in many theoretically appealing UV completions in the standard model, in particular in completions arising from strings, there occur intermediate scale axions and ALPS automatically. ALPS can explain the anomalous transparency of the universe for very high energy gamma rays, and they may explain soft X-ray excesses from galaxy clusters. But what I find most important is that the intermediate scale region in axion and ALP parameter space can be tackled in the upcoming decade by a number of experiments, by haloscopes, light shining through wall experiments, and helioscopes. So stay tuned. Thanks.
Thank you very much. We're running a bit behind schedule, but we'll perhaps just take a couple of questions.
In order for this photon action conversion to explain the apparent transparency of the universe, you need, of course, the intermediate intergalactic magnetic field to be how strong?
Here that I showed you. Let's see. Here it was. There were this here. Here this was. I have not the numbers here, but here was an optimistic magnetic field, optimistic and fiducial. So you need not more. You can do with much less than nanogauss, but
much less than nanogauss.
No, not much less, but order nanogauss. Yeah.
Okay, thank you.
I don't. We have to. I will give you the numbers.
First of all, thanks for a fantastic review. So I just have a question, perhaps you already know, that in particle physics, we invoke singlets, standard model singlets, to hide our uncertainty, hide our ignorance.
Yeah,
okay.
Yeah.
Now, as soon as we have invoked to explain this theta QCD, which has to be less than 1 part in 10 raised to 10 to explain the observations, we have invoked axion, singlet. So how much fine-tuning am I making in this process? Because technically speaking, we have a beautiful mechanism which doesn't invoke this axion, Barr-Nelson mechanism. So why don't we? Why have we given up on Barr-Nelson mechanism?
Yeah.
Which doesn't require. I mean, of course, there is also fine-tuning.
Yeah.
Is it technically more natural?
I think I think in the models where you, I mean, yeah, you are thinking about the, I mean, you could think that you,
I mean, I understand that
Yeah,
axion provides a window for us to look
Yeah,
for it, a new
yeah.
particle.
yeah,
And we can spend money on it, there's no doubt about it. But the physical motivation, which was your second point second, I mean, we equally have some other mechanisms, so why? I mean,
yeah, but yeah.
So could you summarize what the other mechanisms are? You talked
Balance
about
mechanism.
Could you say what it is other than the name?
Okay, so you require, I mean, in the weak sector, you require CP and P to be violated, I mean, to be broken spontaneously. So that's, and then of course, it's really kind of more than, there is an just because it works for anything doesn't mean that you have to have a strong motivation. The strong motivation should come from whether it's technically natural or not. That's what the physics is.
I think for the string axions, for example, I mean, there is no,
Well, at low energy, string theory provides so many degrees of freedom
Yeah.
that it doesn't have a unique
oh, you see,
prediction.
okay, yeah, okay.
It's clearly a very interesting discussion
Yeah.
here, but we should probably
Maybe
defer
we
it
should
to
talk
lunch.
about
Okay, so let's thank all speakers this morning.
Yes.